told you about the spectrum of stuff. Normally we get project scientists and project managers and all of that to give their perspective on space missions that Goddard has launched. Well, that's not the only perspective. There's so many things that go into a satellite mission. And one of them that frequently is missed is the operations phase of the mission. And we're fortunate today to have Alice Bowman from APL, who has that perspective. How do missions look like from an operations point of view? So anyway, Alice is the principal professional staff at APL. She has degrees in chemistry and physics, and she was telling me she had a lot of experience in the hardware and instrumentation end before she ever came over to operations at APL. Anyway, she is a Space Mission Operations Group Supervisor, and she's my son's boss's boss. So I'm going to report to him on how you do. Anyway, she's a member of the Society of Women Engineers. She was awarded the Resnick Challenger Medal from that organization. She's an associate fellow in AILA. She serves on the International Space Ops Committee. And she, I believe, is the only speaker that we've had who has an asteroid named after her. Wow. Good going. Anyway, Elle's going to tell us about the New Horizons mission.
No, New Horizons is not coming back to Earth. So first of all, thank you so much for inviting me to speak to you about New Horizons. I always love the opportunity to speak about this mission that's near and dear to my heart. And let's see, I want to make sure I don't pass my tether here. So this is a NASA mission. It was awarded in 2002. So we make history. So I'll spoil it right away. And you probably already heard about New Horizons, all the really cool stuff that we did. So just a quick overview of the solar system. Average distance between the sun and the Earth is 93 million miles, 1 AU, and it takes a photon from the sun 8 minutes to travel that distance. If you look here on the far other side of the diagram, you can see where Pluto is. When the spacecraft encountered it, it was 32 AU from Earth, and then a very small Kuiper belt object called Arrokoth, which was 44 AU from Earth. So really long distances, and when you calculate how long it takes the signal to get 32 AU or to get to 44 AU, it's quite long. So most everything is pre-planned. No joysticking on this mission. Why did we want to go to Pluto? This is what the Hubble Space Telescope showed of Pluto, our most powerful telescope at that time. Now we have the awesome James Webb telescope, but this is what Pluto looked like. And the engineer in me says, well, I don't know about that. It might be interesting. But the scientist in me says, wow, this is going to be really cool. You can see all those contrasting pixels there, and so you know there's something cool going on. So this was part of the sell to NASA to get a mission to Pluto. So we were awarded the project in 2002. We launched in 2006, and that was quite a feat in itself because it is a nuclear-powered spacecraft. And if you've ever worked on nuclear-powered spacecraft, you know that there's a lot of red tape that you go through to ensure the safety of Earth when you launch one of those. So 4 years is a pretty short time, but we did it. It was with all planetary missions, it's really important that you hit those launch windows, because if you miss them, then it means a longer flight, usually, or more challenging to get to where you're going. And so in 2006, when we launched, we did have, I think it was a 4-week launch window, but we didn't launch in the first 5 or 6 days. It was going to take us an extra 5 years and 7 years to reach the planet. So it was really important that we hit that launch date. And I don't know how many of you were following what was going on then, but we had a storm come through, and it didn't seem like it was a really bad storm. So this was January 2006, so -4 on the 15th of January, and we lost all power to the laboratory. And I can remember them bringing in generator trucks and wiring them into the building power, and frantically they got it all done, and then they scrubbed the launch because there wasn't enough power really to power up all the systems that really in a contingency scenario would be able to support that mission. So we actually launched on the 3rd day, January 19th. We flew by the Jupiter system. We got to the Jupiter system in 13 months, pretty fast, because that's 580 from the sun. Used Jupiter as a gravity assist. It sped up our transit to Pluto by about 3 years. And then still, with that speed up of the mission, it still took us 9.5 years to reach the closest approach with Pluto. And then, so Pluto, 32 AU is about 3 billion miles from Earth. And Arrokoth, we went on to encounter Arrokoth, and that was another 1 billion miles beyond Pluto. Yes?
Could you put the microphone closer?
Oh, sorry. Is that better? All right. I'll try to remember that. Eat the microphone. So our spacecraft is pretty small. It is about the size of a baby grand piano. That big white dish there is about 7 feet in diameter, or about 2.1 meter. We have 7 payloads on the spacecraft, and the spacecraft weighs a little bit over 1,000 pounds. When we launched the spacecraft, we had 170 pounds of hydrazine, and that's all we have. So we were very frugal with that propellant, because we have a long way to go. So challenges, I already mentioned one: distance from the sun, really, really far away, 9.5 years to reach our primary objective. We need a spacecraft that can take care of itself, so that means a lot of onboard autonomous software that's monitoring points, the autonomy system. And power, of course, I mentioned before, we need to have a nuclear power generator for that, because if we had solar panels, it would have to be as big as a football field in order to have enough power to operate. And like all NASA missions, first reconnaissance missions, this is a flyby mission. You only get one chance to get it right. You can't turn around and go back and do it over. So that was a little bit stressful. So just a chart here to show you what our challenges, by the numbers are. For the primary mission, Pluto was discovered in 1930. So we had about 80 years to look at Pluto and learn everything we could know about it from Earth. Still at that, we did not know all the moons that it actually had. We didn't discover 2 of the 5 moons until 2005, and then the last 2 moons were discovered in 2011 and 2012. And then Arrokoth, this very small object that we flew by, was discovered in 2014. So we only had a very short while to know about it, and I'm going to tell you a little bit. We don't run out of time, but I'll tell you a little bit about how we gathered information, enough information to put our command sets together to accomplish that encounter. And now the spacecraft is 5.2 billion miles from Earth, with a light time delay of about 7 hours one way, 7 hours and 45 minutes. And we have transitioned the spacecraft into a 3-axis mode, or a picture-taking mode. And we are doing a science campaign for the next 2 months. So we're still gathering lots of good science data way out there in the far reaches of our solar system. So I'm the Mission Operations Manager, or MOM, and that's my call sign on the box. So I lead the care of the spacecraft. We set up the ground station for the communications. We developed the spacecraft schedule, and if there's anything wrong with the spacecraft, we're the ones that lead that effort to make it all better. So just to give you an idea, so we use the Deep Space Network, and Phil can tell you lots about that. There are 3 complexes around the world, approximately 120 degrees apart. Each one of them has a 70-meter antenna and then a number of 34-meter stations. So there's Madrid, Spain, Canberra, Australia, and Goldstone, California. And our spacecraft is so far away that pretty much the only way we can return science data is with the 70-meter stations. The 34-meter stations provide us with navigation information and health and safety data. So, an exaggerated diagram of what it means to command a spacecraft that's really, really far away. Most of you guys probably already know this, but I'm going to go through it anyway. So we have the ground station on the bottom, sort of grayed out, and this is an example of when the spacecraft is at Pluto. So the spacecraft, we generally send up commands to spacecraft memory that last about 2 weeks, except for Encounter, which is a little bit shorter, let's say a 2-week period. And they're all time tagged, meaning that they're tagged with the time that would, whenever it matches the spacecraft onboard clock, those commands will execute out of memory. So here the example is the spacecraft is overhead, and the onboard clock is ticked down, and it says send a packet of telemetry to Earth. And the antenna, ground antenna could be supporting another mission, but finally the ground station antenna is up, ready to receive information from the spacecraft. And here is the halfway point. That telemetry, this packet is still making its way to Earth. And then finally, a one-way lifetime later, it receives that packet of information on the Earth. But look how far across the sky that spacecraft has moved. So this is the 4 hours, 25 minutes is approximately the one-way light time that we had when we were at Pluto. Likewise, if you want to send a command to the spacecraft, you have to kind of point to where, well, you have to point to where the spacecraft will be a one-way light time later. And then as that spacecraft comes across, that packet will make it into the station, into the spacecraft. So the encounter sequence we developed was 9 days, so that's much shorter than the 14-day period. And there were a number of reasons that we did this. It had to do with, we always have to plan for contingencies, right? That's what you do in operations. You have to plan for what you think are all the possibilities. And so the 9 days came about for when we thought we could recover from an unknown anomaly that we had never experienced before in flight. But the autonomy system was programmed to detect. So it was detectable, but we had never done it before. And so that's how we came up with the 9 days and where those primary objectives were for this mission. So on July 4th, 2015 was our first opportunity to send this set of commands, encounter commands, or the core load to the spacecraft. And the reason, and the encounter would start on July 7th. And you might ask, well, why did you wait so long before you sent the commands to the spacecraft? And the answer is that this 9-day set of commands took up 80% of the memory that we used to hold commands on board the spacecraft. So the 20% left over came up to about 4 days. So once that 4-day, 20% load started, then the memory was free for that 9-day sequence to be accepted into memory. So that was July 4th, early in the morning. We started uplinking these commands. It took 2.5 hours. Even though we were radiating at 2,000 bits per second, which is pretty fast for an uplink. And we had to burn these commands to flash in order to be able to recover from a fault, like a power fault, where we had to reload from memory. So we were going to do that autonomously. About 1:55 in the afternoon, or round trip light time later, in the Mission Operations Center. So again, we divided the team in half. part of the team was uplinking, and they went home and slept, and the other part of the team came in and was watching the spacecraft receive those commands to make sure everything was okay. About 1:55 in the afternoon, so partway through watching the computer on board the spacecraft receive. Remember, we're 4.5 hours. We're looking at data on the ground that's 4.5 hours old. At that point, it looked like everything was going fine, and then we lost telemetry. So if you're in operations, that's the worst thing that can happen. You lose telemetry because you have no information, although we had been up with the spacecraft just prior. So we did have a little information. The engineering side of the team was quickly working to figure out what we had done wrong for that. On the science side, they thought that maybe we had hit something and the spacecraft was destroyed because we have these unknown particles out there. We had a hazard campaign, even though we didn't detect anything. So there were two possibilities in talking with our autonomy engineer. One was a bus controller reset, which is a main computer when you get that little circle thing that kind of sits there, you know, has to be rebooted. That, or a bus controller swap, which we had never experienced before in flight, which the autonomy system, and this is what actually happened, the autonomy system detected that the main computer heartbeat was not present. And it decided that the main computer was, had failed, and it switched to the backup computer. And so we had to wait until that autonomy system had completed the switch, and we started sending out, in this case, 10 bits, or a safe mode type situation with the spacecraft. So once we figured out that that was likely the cause, given the time on the wall clock, one of these took 108 minutes, the other one took 77 minutes for the spacecraft to reconfigure. We were in the 77-minute time frame, so we asked the DSM to reconfigure, and we locked up to that signal, but it was at 10 bits. And so now the question became, what happened? Is the main computer still operational? Because if not, we had to change the polarity of all of our commands that were going to go to the spacecraft. And did we have time to do it with the sequence starting, or that set of commands starting on July 7th? So at 10:30 in the evening on July 4th, we convened our first anomaly review board meeting, which is something that all spacecraft do when they have something wrong going on board. And we had developed our plan. By 3 a.m. on the 5th of July, we sent our first bundle of commands to the spacecraft. So what we did in planning our recovery is we looked at how much time we had a marker from our PI, who's Ellen Stern, of which activities we could sacrifice and which ones we had to come up and conduct. So we had a notion where we wanted to, engage the timeline or start the timeline. And we looked at the time that we had, accounting for the procedures that had to go up to the spacecraft, and we divided that into 4 RTLTs, because that's our metric, right? So we developed our plan to use 3 of those RTLTs, saving that 4th one for just in case we didn't understand something, so it would give us the margin. So we sent our first bundle of commands on at about 3 a.m., actually 3:11 a.m. on the 5th, and waited a round-trip flight time to get response. So the last thing you want to do in operations is make it worse. You really need to, so we sent up a bundle of commands that did a number of things, but when we got the information down on the ground, then we could send up the next bundle. So with about 4 hours to spare, we saw that that spacecraft had transitioned into a 3-axis mode, which meant that it could actually execute the encounter sequence and go on to collect awesome data of the Pluto system. So just that's a story that people always like to hear. So fast forward to July 14th, which is the closest approach day. Down at the bottom of the screen, we have our last contact with the spacecraft that was with the Madrid 70-meter station, or DSS-63. We checked to make sure that the spacecraft looked fine. We got one final image down from Pluto. We called it the fail-safe image in case we hit something through the Pluto system and we never heard from it again. We would have this one last picture of Pluto. So Pluto is tipped a bit from the ecliptic, so that's why it looks like, you know, the spacecraft is flying through this kind of dart board kind of thing. So the yellow line here, or orange-yellow line, is the trajectory that the spacecraft took through the Pluto system. The aim point here is what we built all of our observations to take advantage of the best light for those kinds of observations. We had a clear box around that so we could be off a little bit and still collect awesome observations that satisfy the requirements of the mission. And then we did occultation with Pluto and with Charon, and what we were doing here was looking for an atmosphere. We had actually, at the time, there were 13 DSN stations, 34 meters and 70 meters, and we actually used 7 of the 13, so almost, you know, more than half of what was available. And we trained those antennas a one-way lifetime earlier than the occultation, sent radio signals up to the spacecraft at slightly different frequencies. And so the spacecraft at Pluto, let's see how do I do this and hold it. So if the Pluto is the microphone, or the spacecraft, and then we send these signals up from Earth. Half of them RCP, right circular polarized, the other half LCP. And we watch, onboard the spacecraft, we have a receiver that will receive those radiation signals. And as the spacecraft passes behind Pluto, of course, those signals will go away. And if it hits an atmosphere, you can see some attenuation in those signals. So that's how we did the detection of the atmosphere on Pluto. And then on the other side, 22 hours later, we have contact with the spacecraft. The scientists gave us like 15 minutes because, you know, your best science is collected when you're really close to the system. But we, as on the engineering side, were really curious. We wanted to know, how did the spacecraft do? And so the next is a little video of that night where we were setting up and hoping to receive 15 minutes of signal from the spacecraft and determine the health and safety of the spacecraft. We aren't getting any data down except for real-time health and safety data. And we're looking at the recorder to see if it has filled up as much as we predicted it would fill up, which gives us an indication that if the data collect actually happened. Ops Center is pretty small, but it's pretty full this night. Uh-oh, no sound.
Is the speaker muted?
We tested this.
Yes, I heard.
Should I turn this part out? Maybe? I'll just turn it out. So hold your ears in case this is
And lock on symbols.
So that's the first step. Getting data.
Okay, copy that. We're in lock with telemetry with the spacecraft. Okay. PI, Mom on Pluto 1. We have a healthy spacecraft. We've recorded data of the Pluto system, and we're outbound for Pluto.
Okay, so a very happy PI. I'm gonna, yeah, and a happy operations team as well. I'm gonna turn this back down a little bit. You don't know how hard, or maybe you do, how hard it was to keep those people in that back room. Oops. Keep people in that back room until we ascertained the health and safety of the spacecraft, and then the agreement was once we did that, they could come into the room. But it was a hard negotiation there for that one. Okay, let me see if I can. All right, so how did we do? So you probably didn't remember, but the aim point down there is different than what we were targeting. But realized that we're 3 billion miles from Earth. We had that anomaly that almost cost us the encounter, or part of the encounter. We came in 88 seconds early and 26 miles off the aim point. And I would say that's still a pretty good track record. But I always like to say that we could have done better, but we were a little bit gun shy. We were in the air box, and so we went for it. So this is a picture of Pluto from Hubble Space Telescope. And then here's the picture that the spacecraft returned. So pretty awesome. This is a composite picture of our long-range black and white camera and our spectrometer, full-color spectrometer. So pretty cool. The next is a video that recaps the launch and some of the major discoveries that were made, and then where we're going beyond. And this one is loud. I'm not sure how to adjust the volume once I'm in presentation mode, but if it's too loud, tell me and I will stop it and adjust. Glaciers, mountains, canyons, ice volcanoes, you know, it's got just about everything. So, first extended mission was to continue to explore the Kuiper belt. There was a very small object called Aricot, actually when it was discovered, it was given the name 2014 MU69 and plus probably some other numbers as well. And we thought that that was kind of too hard to go through the encounter with, but we didn't have a formal name that was accepted by the IAC, and so we nicknamed it Ultima Thule. And then it got its formal name a year after encounter, so in January of 2020, it was formally named Aricot. So throughout this presentation, if you hear any of those names, it's all referring to the same object. And Aricot is 1 billion miles beyond Pluto, so that means a longer round trip lifetime. Also part of the extended mission was to not only do a close-up flyby of another Kuiper belt object or aircraft, was to also image other Kuiper belt objects, and these are just a few of those that we imaged. Down there in the corner you can see, I put little pictures here. We used a Subaru telescope in Hawaii to look at the field of solar system objects that are in the direction of the New Horizons spacecraft. And then from that, we down select to a number of potential targets, because we're still looking for another flyby target. Then we propose to the Hubble Space Telescope, which is that cylindrical telescope there in the picture, and propose for a campaign there. And then we look at those objects in detail, get their orbital parameters, and then we uplink those to the spacecraft as part of our observation campaign, and so that we can image those, even if they aren't candidates for a close flyby, they still are candidates for us to image them. And I think this is really cool. It takes less than a year to do that. So here we are, we're discovering and we're defining with the Hubble Space Telescope, and then we're actually observing with the spacecraft. So we have a very well-oiled machine here. So one of the challenges with the observing a very small object really, really far away, and something that was only discovered on the order of 3 years before we have to define a command set to do the observations, because we need time to test and verify the commands, make sure everything is safe and it actually accomplishes the objective. So one of the ways that our scientists do that is by occultations, and you can think of an occultation just like an eclipse. But instead of the sun, you're using a star. And instead of the moon passing in front of the sun, you have our object, aircraft, passing in front of the star, or the occultation star. And so the scientists were able to calculate where these opportunities were. And just like an eclipse, where you are on Earth depends on how much of an occultation you're going to see. Whether that object is going to totally blank out the occultation star or sun, or partially blank it out. So there were 3 opportunities. The first one in June of 2017 was over Africa and Argentina, and we did not see anything. So they went back and redid their calculations, tweaked some things, fixed some mistakes, and the next one was on July 10th. It happened to be in the South Pacific off the coast of New Zealand. So NASA has this plane that they just recently decommissioned called Sophia. It has an awesome telescope on board, and so the coordinates were given to the pilots, and then the scientists got an airplane, and they said, we need to be at this point at this time. And so they arrived at that point, opened up the telescope, took data. But like with any kind of scientific observation, if you only have one observation, it's really hard to collaborate or to understand if you really saw a fluke or you actually saw something. So the last opportunity to get this information that we could use to develop our set of observation plans was on July 17th. It was in Argentina, and in July it's winter, it's on the coast, there's a lot of wind, rain, so not really good for statistics for astronomy observations, but pulled out all the stops on getting with this. I should say that all 3 of these campaigns, we partnered with local universities, and so it was amazing how much support NASA has throughout the world. People will come far and wide just to support a NASA effort, and that's exactly what we saw. So this is the coast of Argentina. That red, you can hardly see it, there's a red line there. That represents the mathematical center of where you should see the full occultation of Arrokoth with the occultation star. And then you see statistically moving out from that center point. All those little blue bubbles are where they set up a telescope manned by 2 people. And yeah, so the next is a video of what that night was like, trying to find Arrokoth in the sky. Parts of this are hard to hear because of the wind. Eventually they put subtitles in there, so I'm hoping that you guys you'll see this. And again, if it's too faint, let me know and I will stop this and adjust the volume.
Tonight is the big event. There's a big star that looks out, but who knows if it's actually going to happen.
So this third occultation feels really important because if we don't catch the object this time, we'll have a lot less information going into the encounter.
I want to just say thanks to everyone for the past few days of work and to some of you for the past few months of work. Let's go get the day tonight.
So pretty desolate.
Well, we're about to start in 10 minutes, all right. Last one, 2-8. Heard something about 269. Horizon supplies past.
How's time? I can within the next minute. And I will tell you if I see the star disappear. I saw it.
No way.
I saw it. I'm pretty sure I saw it.
Holy crap.
I actually saw it.
Holy crap.
No, I actually started reading this year. We as a team succeeded in getting not one, not two, but 5 different occultations. So we saw the star go up and come back as MU69 passed in front of the occultation star at 5 different locations.
I don't care what the weather is today. That's a great feeling. Here it is Tuesday. It's raining, windy, cloudy, really nasty stuff for astronomy. And it doesn't matter. It's great. It can do whatever it wants as long as I can get out of my airport and back to Buenos Aires tonight. It could snow 10 feet tomorrow for all I care. But we got what we came.
Yeah, so you saw all that wind. This is a very small town on the coast of Argentina. And I said before that everybody was really, across the world, so supportive of NASA's efforts. And the scientists were worried that the headlights from the only highway that brings cars and things into that city were going to sort of pollute or degrade the data that they were collecting. And so the mayor said, oh, well, I can close down the highway for you if you like. And they said, you can do that? And he said, yeah. So he closed down the highway for them while they took these measurements. And the wind, you saw how that wind was crazy. He said, well, I have these big panel trucks, and I can give you those, and you can use that to buffet your telescope so you don't have as much movement. So it's just awesome that people around the world are so supportive of NASA, and those are just a few of the things that we experienced going around trying to get this data for this encounter. So how did we do? So this is the first observation on June 3rd, and these lines represent the telescopes looking at the occultation stars no breaks there, it means that the telescope saw the star the whole time. And then here's the Sophia measurement. We only had one telescope, so you can see a very small break there. And then here, the telescopes in Argentina. And it's really cool here. Telescopes I know have become much more complicated than when I was a child. But just to think that you can set up a line of telescopes, observe an object 4 billion miles from Earth, and trace out the shape of an object so very far away. So I know you want to be on the team that collects the occultation itself, but look how much information the other telescopes that didn't see that occultation contributed to this data set. That's pretty awesome. And so here are some of the shapes that our artists came up with, because you're only capturing this object in a snapshot of time. You don't know, and we all know that objects in the solar system have some kind of rotational period, so you don't know exactly which rotation you captured it on. So these were some of the ideas of what this object might be. So fast forward a little bit, and we're 24 hours out from the closest approach with AirCock, and this is what it looks like. Our long wave black and white camera has a field of view of about 8 inches. And so, we were really happy to see this centered in that field of view, because if we hadn't targeted correctly, we could have clipped it off or, not seen it at all, but yet still be really close to it. So then, on the day of closest approach, this is what actually was resolved by the camera. So it turns out it was what we call a contact binary. Interesting thing was, just like on Pluto, we turned the spacecraft to look back at the object, so it's backlit from the sun. And we saw this, which was very unexpected, because if that object were round, you wouldn't see these kind of shadowed pictures. So it looks like, and we've deduced, that is somewhat flat, like a pancake and a walnut kind of stuck together versus round balls, or a BB-8, which is what I thought of when we first saw it. So how did we do? If we correct for, ratios and everything, and we can actually fit aircraft right into the shape that those telescopes predicted that it was going to be. And so then this one is just a little animation that actually a public scientist, Roman, who's been a friend of ours, mission came up with, and so it's really cool. So what next? The spacecraft is traveling in the direction of Voyager 2, not quite as tilted on the ecliptic, and like I said, we're 5.2 billion miles from Earth and are in our observing campaign right now. We started August 5th, and we will end that September 27th, collecting a lot of data that you can't collect when you're close to Earth, because you have this dipole light that's interfering with that data collection. And I'm up here, I'm honored to present this to you, but it takes a whole team of people to do this. And we have a pretty famous member of our team who was actually there on December 31st, right before AirCock encounter. You guys might know who he is. Brian May. He was teaching me how to take a selfie. I didn't know. And then some books for further reading. All ages, little spacecraft that could is good for elementary kids. Mission to Pluto is middle school, chasing New Horizons. It's really kind of an interesting read about not a lot of science, but just how the program came to fruition and all the fits and turns that it took. And then the big book there is a compilation of some of the most unique observation, or most unique science that was discovered. And then if you want more information, this is the website. And this concludes my talk. I'm happy to take any questions from you.
So what are the challenges involved in the work cloud?
So what are the challenges involved in the Oort cloud? Is that what you said?
Yes.
Yeah, so the Oort cloud is really, really far away. We'll never get there. Well, we'll get there, but we won't have power to turn around and broadcast anything back to Earth. It's like 120 some AU from Earth. And so yeah. We expect with our RTG right now, you saw on that slide, we have about 175 watts of power. And we are working on our baseline, to lower our baseline power concept. We've already done it so that we can extend another couple of years, but we're continuing to work on that. We're hoping to get to 80 or 100 AU, so we're still going to fall short of the Oort cloud in terms of spacecraft will go through it, but we won't be able to bring the data back. Yes?
Do you know what the return telemetry bit rate is?
I sure do. So the question was, do I know what the return telemetry bit rate is? And you mean currently? Currently? So 5.2 billion miles. When we were in 3-axis, we have power to downlink the data and only turn on one transmitter. So using the 70-meter antennas, our 10-degree elevation rate is about 300 bits per second. When we are in spin mode, we have a little bit more power, so we can turn on 2 of our transmitters on board the spacecraft. We use a piece of equipment at the DSN. Each complex only has one, and I hear that they're going to add another one, which I'm ecstatic about. And it's a piece of equipment that can combine 2 signals coming from a spacecraft and essentially almost double your data downlink rate. So in that case, we're at a little over 500 bits per second when we're in spin mode, which is what we normally are in, and that's at a 10-degree elevation.
How long does it take to that image you showed of Pluto?
How long did it take that image of Pluto to come back? It took, at that time, we were probably at about 2K at our maximum downlink rate. So each part of that took about 6 hours to come down because it's a composite, so about 6 for each. And it kind of depends on, we do have data compression on board the spacecraft, so it kind of depends on how that data gets compressed. Yes, Phil?
Yeah, so I was trying to remember, it was a long time after the encounter to actually downlink, from memory, downlink all of the images. How long was it again?
Yeah, so we completed the encounter on July 16, 2015, and we completed the data downlink on the end of October, I think it was like the 20th, in 2016, so about 18 months to downlink the data. And that's an interesting story. People kept saying, are they hiding stuff from us? Because we post the images to the website, but it just took so long to get the data down that we weren't trying to hide anything. It's just that it just took that long to get it down. Yes?
How much fuel hydrazine do you have left? What will you use it for?
So how much hydrazine do we have left and what will we use it for? We have a little over 9 kilograms, and that is about the amount we use to do the Erikoth encounter. So we are still looking for another target, another flyby target, but we are pretty much out of the theoretical Kuiper belt, which is supposed to end around 50 AU statistically, and we're at 56 AU from the sun, 55 from Earth. So chances are kind of small that we're going to use it for that. So we have lots of other experiments and observations that we're going to use the propellant for. So. Yes, Bill?
Not a question, but just a comment for everybody. If you want to see more about this mission and the science and all the things that you talked about, there's actually several really good NOVA programs on public broadcasting that will tell you a lot about it. And you get to see Alice too.
Yeah, so thank you, Phil. There were quite a number of programs that were filmed when we were either pre or post encounter, and occasionally now we still get some requests. So, yeah. And I saw, yes.
I wasn't sure path that was on, whether you actually went all the way past the Kuiper belt. If you did, have there been any estimate of how extensive it was, so we might get another clue towards what the total composition is and maybe what the origin might have been?
So the question was, did the spacecraft go through the Kuiper belt? Were we able to determine any characteristics, including the formation or origination of the Kuiper belt? Did I get that right? Generally speaking. Yeah, generally, okay. So again, the spacecraft has a fairly narrow point of view. So the part of the Kuiper belt that we flew through, you could see that we did do imaging of other objects. And I know when you see pictures of the Kuiper belt, it looks like it's very congested, but it's not. There's a lot of stuff, a lot of space in between. We know that the Kuiper belt is composed of these, what they call cold classical objects. It doesn't necessarily mean they're cold, but they are. It just means that they haven't been disturbed like comets and things that are disturbed from the orbit, come close to the sun, so they have this heating, cooling cycle going on. These objects in the Kuiper belt are left over from the formation of the solar system. So that's why it's really cool to go and study them and see what they're like. So that's about all I can say. Yeah. Yes?
So I'm guessing the sunlight at that distance is pretty dim. So what kind of issues did you have with imaging in that amount of light?
So the statement was that the sunlight is pretty dim at the distance that we are right now, and do we have any issues imaging in that very dark space? We have a number of f-stops on our instruments, and so we can tailor it to that. We are looking into the darkest part of the sky. One of the things that we are trying to determine is if you're an astronomer or in that astrophysics field, there's this whole thing of what is the background light, what is the level of that background light, and we're actually trying to contribute to that because there's a certain glow that just comes from the stars and planets, solar system, and if you know what that is, then you can use that and subtract from whatever you're looking for and actually do some pretty interesting calculations to come up with some unique information. So that's sort of a tangential response to your question. We have never observed something that we could not see. Now, I say it that way because I don't believe our scientists would have us observe anything that is below the magnitude that we can actually see, or flipped around. But yeah, so we do have a detectable limit. I can't remember what magnitude that is, so we can only go so deep. Yes?
How big is your flight ops team?
How big is our flight ops team? So we are maybe not quite 10. Yeah. And we have pieces of people, so that's FTEs. And so, yeah.
Any other questions?
One more. I'm just surprised, Alice, that I'm thinking as a reference Voyager, which is 46 years in space now, and they've got a nuclear power source that they're, and they've been very creative, I guess, at producing power and continuing to provide science.
Yes.
46 years into the mission, and I still understand. The last I heard before I retired is they probably have another 5 or so years, or maybe more.
Yeah, they keep extending it.
They keep extending it, and they just keep finding creative ways to keep the thing alive, and shut off instruments that are no longer high priority science. And I'm kind of surprised that you don't think that New Horizons, you can do the same kind of creativity.
Yeah, so we are doing, so the statement was that, I think it was, how come New Horizons our horizon for when we can't turn around and have enough power to send data back to Earth is in the, let's say, 2040s. So from launch would be 2006 to, so that's 34 years, something like that. And why can't we, look forward and say we can operate for Voyager, which is, I think it's on its 47th year of operation. And, that's what operations people do. We just recently increased our expected lifetime by about 3 years, 3 or 4 years. Voyager has 3 RTGs. New Horizons has 1. I would make the argument that Voyager components are probably more power hungry than New Horizons just because of the technology. It's a good aspiration. We always look to Voyager for inspiration. I hope we do get to 47 years or whatever. So good point.
All right, let's thank Alice for reading.